In the last video, we talked about the internal structure of a neuron and its connections with other neurons. It looks really complicated, but the calculations involved are actually quite simple. The only mathematical operations involved are just the multiplications, additions, and the application of this nonlinear function, which usually has a very simple form. Actually, later on, once we actually start to see concrete examples, you will see that all those choices for this particular nonlinear function actually has a very simple form, right? It's very easy to use, even though they are nonlinear, but they are actually very easy to use. So, but why is this specific construct useful, right? A single neuron is useless, but if you connect many of them together, they can really do amazing things. So here's an example of a very, very simple neural network. At the bottom, we have an input layer, which contains just the input data. So those are data that we feed into this neural network. Those are input data. Those data are given, basically, right? It's a given data. So those things are provided to us, right? We can assume they always exist. Layer 1, this layer, layer 1 is called a hidden layer. And the reason it's called a hidden layer is because this layer is not exposed to the user of this particular neural network. So the user of the neural network are only exposed to this particular interface, the input layer. They can only put data into the neural network. That's the interface with the user of this neural network. All those layers that's in the middle are called hidden layers because they are not exposed to the user. And then layer 2, that's the topmost layer in this neural network. That's the output layer. So which gives the user of this neural network a set of output data. And in this particular example, the output data has only two numbers. This number, y12, the first output, the output from the first neuron in the second layer, right? If you still remember the index conventions that we talked about in the previous video. And then the second number is y22, which is the output from the second neuron. That's the subscript from the layer 2. That's the superscript, right? The internal calculations are no different from the calculations we talked about in the last video. So each logit, these are the logits, right? These are the logits, those z's. Each logit is just a weighted summation of the input data into this neuron. So for example, z11, let's look at z11, right? So z11, how many? That's the logit of the number 1 neuron in the first layer, right? So how many arrows are pointing into it, right? We have like 3 arrows, 3 lines, 3 connections that goes into it, and each of the connection is connected with one of those inputs, right? So z11 is what? Z11 is just a summation over I goes from 0 to 2, right? So it's wi1 xi, right? So if we expand this particular summation, what it actually means, right? It means w01, this weight multiplying this particular input, w011 multiplying x0, plus w11, that's the weight along this connection, multiplying with x1, that's this input, and then w21, that's this weight multiplying x2, right? You just add them together. X0 is set at 1, right? And then you can just if you want to sort of simplify it a little bit, you can get rid of this x0, right? Because x0 is set as 1, right? And then z11 is just a summation of these three terms, the three connections that goes into this particular neuron, right? So why do we have this particular neuron that's x0 equals to 1, right? That's the so-called bias term, right? And we see another bias term here in the hidden layer also, right? We'll talk about those biases later on, but for now, let's just ignore them, right? Let's just treat them as some kind of a normal neuron, right? But they are actually the so-called bias term. But anyway, that's an aspect that we will not get into for now, right? So if you look at other logits, right? For example, Z12, it's got like three arrows pointing into it, right? So it's W012 multiplying Y01 plus W112 multiplying Y11, and then W212 multiplying Y21, right? You add those three terms together, then you're gonna get a Z12, right? It's all those just multiplications and summations. It's just very simple calculations. The weights W are associated with the connections that comes into this neuron, right? And then go from the logit to the output of this neuron. All we have to do is to just apply that nonlinear function f onto the logit, and we obtain the output y11. Right? You can think of this nonlinear function as just a black box. You send the logit into it, and then you get something out of it, right? You can think of it just as a black box. But why is such a neural network useful, right? Its usefulness actually lies in its capability to make predictions. So, for human beings, there are two different ways of learning. One is rule-based learning. The other is example-based learning. The primary reason for us to go to school and take classes is to learn some rules. For example, we take math classes to learn the rules about how to operate on numbers. We take physics classes to learn the rules about how everything in the universe sort of operates, right? But learning those rules, by learning those rules, we can make predictions. For example, you go to a supermarket and collect a bunch of items into your shopping cart. If we know the rules about how to do additions and multiplications, then we can predict what the total price will be before we check out. The rules themselves are not really that useful. It is the predictions made using those rules that are useful. So if you have a calculator in your pocket, even if you don't know the rules about addition and multiplication, you can still make a very accurate prediction about what the total price will be using that calculator in your pocket, right? That's rule-based learning. The other approach of learning is to learn from examples. This approach is different, but the purpose is the same: to make predictions. Predictions that are as accurate and precise as possible. I myself grew up by the sea. I saw experienced fishermen predicting the weather next day by looking at the clouds in the sky very carefully the evening before. Those fishermen had no training in sophisticated atmospheric sciences. Yet, they could make quite accurate predictions based on many years of experiences. You can imagine at the beginning, when they had very little experiences, their predictions were probably not so accurate. They must have made lots of mistakes. But those mistakes they made must have created some kind of a feedback in their brain, which prompted them to make adjustments to whatever prediction schemes they were using. So those many years of experiences provided them plenty of examples, plenty of data, and also plenty of opportunities to learn from their own mistakes. So deep learning using neural networks is actually the computer trying to learn from examples. So suppose we're trying to make predictions about, for example, the average number of views per week and the average number of likes per week for a certain YouTube video. Based upon, that's our output, right? That's our output. Based upon what? Based upon the input. The input is going to be the number of man hours for making a video, and also the category of the video, of the video's content, right? Suppose we would like to sort of make a prediction about the average number of views per week and the average number of likes per week for video based upon the number of hours, man hours for making that video and the category of the video's content, right? Suppose we would like to make this kind of predictions, right? So we are given this set of inputs. These two numbers are known to us, right? But these two numbers are not known, are unknown, right? And we would like to use this network to make a prediction of it, right? So we don't really know how to write down the functional dependence between the output and the input. So can you write down a function about with the output as the output of the function and with this input as the input of that function, right? Can you write down on the paper a specific formula for doing this kind of a calculation, right? It's not obvious to us, right? We don't really know how to do that. But suppose we have lots of data from previous videos made either by ourselves or by other people, and for each previous video we have a record of the number of man hours used for making that video and the category of that video's content. And also, we have a record for the average number of views and likes per week for that previous video, right? Then the question is how we can use this large data set to train our neural network. You can imagine during this training process, at the beginning, when the neural network, for example, is exposed to, for example, a small portion of the entire data set, right? The neural network only sees a few data, right? The predictions then the predictions made by this neural network is probably very poor, right? But suppose if we can establish a certain feedback mechanism, such that every time the neural network makes a mistake, it can make some adjustments to its internal wiring accordingly. Then, after seeing more and more data, the predictions made by this neural network will become more and more accurate. So for this particular neural network, its internal wiring is actually represented by the weights associated with all the connections. So we have 12 connections in total in this network. So there are 12 weights. At the beginning, we will just assign a random number to each weight. So we just come up with 12 random numbers, right? And then assign one random number to each of the weights. And using those completely random weights, we can compute the output using this neural network for a given input in our dataset, right? Because all the weights are specified. F is given. We have picked a particular F, right? The logits can be computed by using this particular summation, weighted summation, right? inputs x is given, right? Weight is given by those random numbers, right? So the output can be computed by using this neural network, right? And then we can compare the computed output with the actual number of views and likes per week for that given input. Don't forget, this is for a previous video, right? For a previous YouTube video. So we have the input and also the actual average number of views per week and the actual average number of likes per week, right? So those data were actually given in our dataset. This is for a previous video, right? So based on the input, we can compute an output using this network, and then we can compare our computed output with the actual output, right? The actual number of views per week and the number of likes per week, right? And there will be differences. And those differences will probably be very big at the beginning, right? But if we can build a feedback mechanism such that those differences in the outputs can be used to make corrections to those weights, we can then improve our neural network gradually as the network sees more and more data. This entire process is actually quite similar to playing the hot and cold game. In this game, one player hides an object somewhere in the garden, and the other player tries to find it by moving around and asking whether he is hot or cold. The hotter he is, the closer he is to the hiding place. The hidden object we are trying to find here is the best set of values for all the weights in this neural network. How hot we are is given by how close the computed output by our neural network is to the actual output. So when we are playing the hot and cold game, the trick is actually to find the correct direction along which the temperature or the hotness keeps increasing. In later videos, you will find that the approach for finding the best set of weights is actually very similar to the approach that we are taking for playing the hot and cold game. We also need to find the correct direction along which the difference between the computed output and the actual output keeps decreasing.